Lab 11. Buoyancy force in gas. Property of air approximately follows the ideal gas law if you have a small amount of it. Like in the air trapped in a bottle or syringe. On a large scale, however, like several miles above the ground or into the sky, the effect of gravity must be taken into account, in addition to the ideal gas law. So, in order to correctly explain the air pressure's dependence on the altitude, which is the height or distance from the ground, okay. And in other words, if you want to describe the air extends from the Earth several miles above, and then ideal gas law and should add the other effect of the gravity increasing with latitude. Intuitively speaking, there are two factors: gravity, which always tries to bring the molecules down to the ground, and the thermal motion, the speed, the kinetic energy, which tends to shoot them into the sky. So the interplay of these two factors, the thermal energy, the high speed, because one end is open, the other outside is ground, so it goes to the outer space. Then the other side is the gravity is always bring them down. The balance between these two factors give rise to a change of the pressure with the altitude, which means pressure versus altitude, and temperature relation, which is this relation. Okay, think about this. This is like pressure on the ground, and this exponential function. Exponential function means it's a decreasing function. See, with the height goes up and then the pressure goes down. At the same time, when the temperature goes up, and then the pressure always goes up at a certain altitude. Okay, all right, it goes down. Okay, it goes down. Yes. So look at the exponential function. Although this relation derived purely from the ideal model experiment and mathematics, it is very close to reality. It is, in principle, most instruments are based on for trying to find the altitude or gauge or airplane, etc. And the objective of this lab, this simulation let us explore the property of gas when the effect of gravity explicitly taken into account. And our object is a balloon in a chamber, of course, which also same time simulate the gravity. And you will have insight of many phenomena involving gas and the gravity or buoyancy force on balloons and etc. Okay, what are we going to use? We use this software. There is one already included in the folder. If you have a PC and you double click it, if you have a Java installed on your computer, this will automatically work. Or you can start from here in this link. I'm starting it now. Okay, here I started. If you don't want to use the included online version, you just want to use this one. You don't have to download anything, just click this one. Here you go. You have actually several choices for some other thing. Actually, we already did one of this with this one. And this time, the first thing to start with the hollow sphere. And so this is like a sphere, it's hard. And you can inject, now it's a little bit fancier. You can either inject the particles, heavy or light. Now we have two kind of particles, one heavy and light. Okay, as far as the pressure is concerned, and for ideal gas, it doesn't matter heavy or light. But whether a balloon will fly or going up, it does depend on how heavy the balloon is. So that this experiment let you see their relations. So you can go over here. So inject the gas into the sphere. So it's a light species. Okay, you put say 23. So you see things are going into the sphere, right? So the sphere itself has a weight and it goes down to the ground. And then if you have now at the same time you can pump into something outside, and then you see, and now Now you probably see an explanation why balloon goes up. And then if you have some temperature, and then these are pressure is due to collision, and you will get a question in exam. What is actually the original pressure? You'll say molecular collision, because it bumped that balloon up. Okay, there's a condition, there's a gravity. So you turn on the gravity, a little bit more gravity, the balloon drop a little bit, but it still go up. So gravity is over here. So, and then of course, if you make it colder, that bumping force is less, so it's dropped lower. Okay, and even colder, eventually even colder, you see, and it may eventually cold and touch the ground. I add ice to cool it down, and its particle has weight, and then still bumping up outside, but then of course bumping from the bottom up, and then this not will be cancel its weight, so it touches floor. But then if you heat it up, and you see the explanation is the air outside will heat up, then there's a pressure difference between top and the bottom. Up on up, and there is nothing. So if you heat it up, and you see, and it all heat from the bottom, so it lifts the balloon up. Okay, and lift the balloon up, and if you heat it higher and higher temperature, but there's always stronger pressure, and then some go beyond it. See, there's a temperature is higher, there's always something from the top to try to knock it down, but there are more pushing it up than those who try to knock it down. See, there are some balls, kind of think of like a soccer ball, try to knock it down, but then there are more, so the overall, and that's, we interpreted that as a pressure difference with bottom and top. See, there are top balls try to always hit the ball down, but then the bottom ones are hit the up. So that actually counter the gravity, so it goes there. But if your temperature is lower, so you just see it will be. But now, if you, but there's another factor is how heavy is this ball. But if I put more heavy species into the ball, say add 200 of these inside, even if it's bumping, it still cannot do it because that thing is heavy. So now it's bumping from top up. There are less on the top, more from the bottom, but it still dropped to the ground. So there are 3 factor or 4 factor into play: the pressure inside, pressure outside, how heavy it is, and what kind of species in it, and also the temperature. So, and this lab is actually for you to play with, and not much calculation, but gain some important insight. And then, of course, I will let you do some calculations in the lecture, the course. Before we go further, I will just preview about what we're going to learn in the class, which is, so that's this topic. We will learn, maybe we already have learned, or we will learn tomorrow or sometime. So it is about liquid and or the floating force, okay, buoyancy force, and that's very important. If you think about something, this is like a sidebar, whether you will be floating on the water in a boat or sink the water, what decide this? Or decided by the Archimedes principle. When an object is immersed in a liquid, the buoyancy force, the total floating force, is acting on the body is equivalent to the weight of the fluid displaced by the body. What does that mean? Which means, why there's a force of pushing things up. Okay, imagine we talk about the pressure in the liquid is the isotropic, which means the same directions, all directions, but it depends on the height. Imagine you have this water ball and this, and then on the bottom, we go deeper, it will high pressure, so the force all in perpendicular surface, the force is this way. But it go up, the pressure is lower, so the force pressing it down. But there are stronger force at the bottom and the weaker force on the bottom. Overall, there is a force that goes up, right? Okay, if you think about this is the water ball, the force goes up. Okay, and that's exactly the origin of the buoyancy force, which is floating force, you can say, yeah, pushing things down. But if this ball is actually a water, well, it does nothing, because, well, the water itself has weight, so if that exactly cancel the weight, so nothing happens. So this is imaginary water ball immersed inside here. But now, but it's exactly, we do analyze in the class that this force overall is exactly, here's more, here's less, overall is more. How much more floating on this? Well, exactly equal to the weight of the water. So outside is water, inside is water. Therefore, nothing happens. But now, same thing if you replace here on the right with the cannonball, which is much heavier than that weight of that same size ball of water. So then you still got whatever force of the floating force, but it cannot cancel it, and it will go down. But now, if this ball is replaced, instead of the iron or steel, replaced by a piece of wood, or oak wood or something, which is much lighter than the same size of the water, and then the overall force, the gravity will be less on the wood, so it will float up. So what decides an object will float or not? Just compare. If it's heavier than the same size piece of water, it will sink. If it's lighter than that same piece of water, and it will float. So that's called Archimedes principle. So remember, water will flow. Imagine an object. See, if I throw into a lake, will it sink? Well, imagine that piece of ice. Okay, is it bigger, heavier than that piece of ice? If it's heavier, it will sink. If it's lighter than that piece of ice, then same shape, same structure, and then it will float. So that's the idea. All right, so then why do I talk about this? And back to our, and in the air, it's the same thing, okay? Something like a balloon. So therefore, you seldom see anything float up in the air, because it displays the air pressure difference between bottom and up. There is a difference, but very little. And so nothing floats unless you have something very light like a balloon, which displays a lot of air, so the difference will show up. They have a very light thing, it will float in air. So now that's what we are going to experiment here. So for the air, the same relation, okay? Same relation. So you have to have lighter, but it still have to have some volume. So now let's back to this lab. First lab with the rigid hollow sphere. First, we will click this rigid hollow sphere and then do the experiment. Then you will do first experiment in inject something into the sphere, okay, but nothing in the chamber, and vary it, and you just observe. The good thing is that this one is easy, and you just have to observe. Of course, be diligently do work and do all the experiment. Okay, this is what I choose. You can choose differently, but as long as you think it's interesting. And so I choose different number of particles in this and observe at different temperature, and what you see. Explain what you observed. For example, let me just do one. For example, nothing in the chamber, first one. Say 10 light species. 10 light species over here in the chamber. Sometimes this doesn't work. For example, 10 light species in the chamber. Okay, and then go. So 10 light species chamber, and you will say, well, if I have high temperature, we go higher temperature, and it just move faster. So inject the 10 light species in the chamber, and you can adjust its temperature and see what happens. And well, this is just like an ideal gas experiment, nothing much interesting, but then you can add more, and then you can watch the pressure and of course in the gravity, but then I just watch. And so this part is easy, don't do any calculation, just put explain. So 20 in there. So this is actually a experiment to try to see what's going to happen. So when a higher temperature move faster, the pressure outside, the pressure outside is 0. Of course, that motion is thermal motion, and it has gravity because it's bumping inside. So there is the chances goes up, same as the chances goes down, but more likely it goes down because the shell also has some weight and bring it down. So that's this part of the experiment. And go as much as 500 and too hot, light to blow up and things. And then part B is different. You have molecules both outside simulate the air, and inside we have different thing in the sphere. And you observe at the temperature, you just fix the temperature and see what happens. And you try to adjust this so that this, the balloon will float up, will ascend, goes up, or goes down to the ground, and we'll see what's happening at different temperature. And just explain what you see. Just say one word. And this is really a lab. And so 500 heavy species. In why heavy? Because you want lighter in a balloon. So heavy in, so they're heavy. 500 of them. So immediately you see it bumps the balloon up. Now, and then you at the same time you put something inside the balloon. Okay, and 10 inside the balloon. Sometimes it's not responding. So you put 10 inside first. Sometimes this doesn't work out so well, but you just have to try and error a couple of times and think the standalone version will work well. And then same time, so that's inside simulate, and then outside you want the heavy species to stay at 500. So outside is 500, and then you see outside you have the gas. So immediately you see the balloon and push this, and then you will have the bottom ones hitting. There are more on the bottom and less on the top, so it flow up. But now if you keep on adding more, as I want you to do, in the inside the sphere, and see what's happening. So now let's see. So now instead of 10, let me get say 50. So there are 50. So I see it dropped a little bit down, and then try to see what's happening, and just say same temperature, and also how about 300, and try to play this. I don't have a specific goal, trying to see explain why it flows, but if you let the temperature drop, and so there's pressure, so there's, you think about the molecules at the bottom, and it's not jumping that much, and so there's even though there's a difference between top and bottom, but even at the bottom they are not moving much because they collide each other. Eventually if the temperature drops down, it will sink. And of course if you even put some heavy things in the chamber, say 200 heavy stuff in the chamber, it would drop, right? So that's why the helium balloon will flow. So it's dropped to the ground. But then if you go heavier, but even at higher temperature, because inside and outside, see the pressure on the top is still lower because there's less air on the top than on the bottom. But the weight of the sphere itself and bring it down. So, but now let me remove those heavy thing, say 0. So 0 light species. So now, okay, let me do 200 light species and then 0. Okay, so in this case, it may lift it up. You see, slowly. That's the simulator slowly floating up, because on top it's knocking down, but it's not that heavy. So the bottom. But if you cool it down, so it's not that active. So that's interplane, and that's the balloon. So, and this is just, as I said, just a play. So in here, you do all those different combinations. You observe that different temperature, what you see, explain, and try to get the balloon to flow high and low at different temperature. But then I want you to explain what you see and explain what's going on. Yeah, what you see, put in here. For example, if I see a balloon flowing because outside, because the air outside, the molecules outside bump, pushing this thing up, and the weight is not weight being cancelled by the air molecule from the bottom, and so on. Okay, and then next one is more specific. I want 550 in the smaller, less in the sphere, and 500 in the chamber, and then gradually at some temperature like 300, 400 degrees, and then gradually reduce temperature and see at what temperature the sphere sink to the bottom. Okay, lower and lower, lower, and see what happens. So 50 in the chamber, 500 in this outside, and you see it's floating, and same thing. But then if you reduce the temperature, and because the chamber itself, and we reduce temperature because the balloon, the shell itself, has some weight, and it will drop to the bottom, right? Because the difference between the pressure, it's like something floating in the air. We're not counting the pressure, and it dropped to. But, and how about if you have so that's the experiment I want you to do. Then how about some heavy one thing in the maybe 100 heavy one also in the bottom. So it's automatically at some temperature. To make it fun, you can use your own choice, change the lab. So of course, in this case, if you have a higher temperature, see if it goes up. Well, nothing happens, because if you have pressure, so there was something bumping from the bottom, there was a lot of things knocking down too, right? So it's not that simple. So physics, C part, I just let you play. Now experiment 2, helium balloon part. You need to choose this tab. So it's a helium balloon, and this outside is heavy, supposed to be air. Actually, helium balloon is this one. So if it's elastic, if you give some air inside, it will expand because there's nothing there, right? If you put some number in the balloon, so it's 20. So it's will go up, because it will go up and up because there's nothing outside, right? If you have something outside, say 200, so then of course it will get squeezed smaller, right? If you have 400 and it's a higher pressure, if it's a PV equal nRT, that ideal gas law, and if you have N is big, the pressure will be big. So if you say 500, and the balloon gets squeezed smaller, and that's this one I want you to play. You can play with different combinations, different configurations, and so on. In particular, add 200 heavy species into the chamber first, and wait until it subsides, and then add 45 helium particle in the balloon. Watch the process, and watch the process when the balloon goes to equilibrium. All right, and question what happens, what's the final temperature, and so on. So first 200 into this, but you should wait until it's balanced, and then add over here 45 helium atoms. Okay, and that's I just tried to come up with it. You can use different one, helium atoms in the balloon. So the balloon, that's the helium. This helium atom is smaller than the heavy atom, so it will flow. That's why you fill the balloon with gas, but it's lighter than the air, so it will flow. But if it's heavier than air, it will not. Okay, so the balloon will be big, but so then you will see. So you can also answer those questions, and the temperature will never be constant because that's microscopic in nature. The object is already continuously moving. Remember, temperature is nothing but average kinetic energy of this. And think about it, just focus on one of them. The average speed. The speed is always changing. It gets bumped into or gets accelerated or deaccelerated, but the average is the temperature. The average would never itself. It would never be a constant. So, and then what's the final equilibrium temperature? And it's like 600 degrees and so on. Why doesn't the balloon drop down? You can see clearly. So the gravity, but see at the bottom, the air molecule keep on heating up. Okay, keep on heating up. But this balloon is big enough. Inside there was some heavy helium atoms, hold this big, so that collect a lot of force from the bottom. On the top, there's always also forces knocking it down, but less. You see, on the top part, and it was try to knock it down, but it's less. And then if you slowly reduce temperature, on average, all will be slower, and then the weight of this object and will be overwhelm these bottom hitters. So then the balloon perhaps will sink. And on the B part, slowly reduce the temperature down and observe what happens. So it's starting at something like 600, and now you start adding a little bit ice to it and see it's less, right? It's less pressure. See, less pressure and less pressure at the bottom, and also less pressure at the bottom. The difference becomes smaller. But then the weight of the balloon starts take effect, or it becomes more significant. You slowly drop the temperature, slowly drop the temperature, and slowly drop the temperature, and so on. See, same number 45, and then at lower temperature it becomes smaller. You should explain why, because it's less pressure and less smaller, and then at about 45 degrees or something, it touched the ground, because the balloon has its weight, this molecule has the weight, but of course, even though this thing is still pushing it up, but it's not a counter balance this weight itself. Now if you start heating up, okay, the condition for a balloon to flow is that inside it also have the same pressure depending on temperature, but the weight of the inside is lighter, and of course the balloon itself also has the weight. So important is to have lighter species inside, heavier species inside, heavier species outside. Now, just to have experiment, if you have heavier species inside, then the balloon will never flow, never ascend to higher altitude. And I want you to increase to 200 and slowly lower the temperature, observe what's happening. But increase, obviously more air, the balloon become bigger, and of course at what temperature drop to the ground, and probably the same, because as 46 it dropped to the ground. The last experiment, now that you already know this, I don't want to demo anymore, just this last question. You want same numbers in the chamber, but vary the number of particles helium in the balloon, and see if the balloon actually sink or not, and that's a puzzle I want you to see. I don't want to show it anymore. And of course, here is some extra credit, and I want you to explore. At one condition, the balloon will ascend to the air. I explain in terms of weight and pressure and temperature. Well, the condition is simply the pressure difference from bottom and up will result in a strong enough buoyancy force that will cancel the weight of the balloon. Okay, and that will translate to the weight, but the pressure will strong enough to push the balloon big, but the weight should be smaller, weight should be less. So therefore, you should use lighter species inside. If you use a heavier species, for example, you just use an air balloon and it will never fly. You have to fill the balloon with hydrogen. Hydrogen is the best. Helium is the second. Probably just these two. Other gases will never flow. Or with hot air. Okay, a hot air balloon. Hot air has the same weight, right? Air has the same weight, but it's hotter and make the balloon bigger with the same weight. So they will take more space and then they will flow. Okay, that's why the hot air means. Hot air means same. Both inside and outside are air, but inside air have stronger pressure, will be pushing the balloon bigger. It's bigger, so they display more air. So the difference between up and bottom will lift the thing up. That's the philosophy of hot air. Okay, and that's the first one. And the second one, calculating this one, I want you to explore. Actually, in the air, you have a calculator. So that's online. So go up in the air at what altitude and what's the pressure, and then you can see how 1 liter volume, a balloon of 1 liter in volume can fly. And if you want to make a balloon that can lift a person, and what must be its minimum volume? So you must have a bigger balloon. Okay, and to do a calculation, this question is more involved, and if you interested, we can have a discussion. Okay, right? All right, that's about this lab. Okay, hope you enjoy it. Bye bye for now.